Hello friends, in this video I'd like to solve 7 problems from this year edition of the AGH University Olympiad for high school mathematical students. From the first round, if you don't know anything about this Olympiad, it's one of Polish Olympiads, but it's better to be called just a competition because it's nowhere near the level of difficulty of Polish National Mathematical Olympiad. It's organized by one of Polish top universities, one of the best Polish universities, AGH, Akademia Górnicza-Hutnicza in Polish. It's a university located in Cracow, and this Olympiad is meant for high school students who wish to study in this university, because this Olympiad has 3 stages. First stage, first round, students solve problems at home and send them to committee at this university, which checks the solutions. The second and third round are held at this university, and students are every stage they are solving 7 problems. First 4 problems are graded from 0 to 10. The last 3 problems are graded from 0 to 20. So 100 points are to be achieved. And for every round, students who achieve 70 points or higher are qualified for the next stage, for the next round. And the exception is the final round. There is gradation for the final round. There are 3 places to be held. First 10 students, I believe, have the highest reward. They can go basically to any university course at this university as they wish. The second best 10 students are free to go at most of the courses, and students who achieve 70 points or greater are given free access to some courses. As I said, this Olympiad is nowhere near Polish Mathematical Olympiad. It's a rather standard competition. Problems are rather standard, but as you will see, this year edition, problem number 6 is very interesting. The rest 6 problems are somewhat interesting, but 6th problem is very interesting. It's from Combinatorics. We shall see in a moment. And one more thing, I wish to do a follow-up on this video, because tomorrow there will be second round of this competition, and I will probably cover problems from this second round once they are published. Okay, so without further ado, let's get to it. Problem number 1. We wish to prove that cube root of 6 minus cube root of 5 is irrational. Here are my hints for this problem. Suppose to the contrary that number x, which is defined to be this difference of square of cubes, is rational. Consider x cubed and recall the following well-known formula that a minus b cubed is a cubed minus b cubed minus 3ab times a minus b. And at some point you may wish to show or write that it is obvious that cube root of 30 is irrational. If you wish to prove that, you may wish to use the rational root theorem. So give this problem a try, and I will see you in just a minute. Okay, so as I suggested, let x be equal to cube root of 6 minus cube root of 5, and suppose to the contrary that this number is rational. We will get some contradiction along the way. What I wish to do is to take cube of this number. If I take cube, what do I have? Well, I have as I suggested, it's cube root cubed minus cube root of 5 cubed minus 3 times cube root of 6, cube root of 5, cube root of 6 minus cube root of 5. It's very easy to verify this formula. And now, on the left-hand side, we have x cubed. Here we have 6 minus 5, it's 1. Here we have 3 cube root of 30. And this number in parentheses, if you look closely, it's just x. It's just x. And now we can write that cube root of 30 equals what exactly? 1 minus x cubed over 3 times x. Obviously, x is not 0, so we can safely divide it. And now we have a problem because notice that cube root of 30 is irrational. I will justify it in a moment. But the right-hand side, 1 minus x cubed over 3x is rational because of our assumption that x is rational. So we get a contradiction. Which basically means that our number is not rational, it's irrational. QED, quite easily done. And how to justify? Because I use the fact that cube root of 30 is irrational, it's obvious, but if you wish to prove it, well, notice that if, for example, if y equals cube root of 30, then y cubed minus 30 equals 0. So cube root of 30 is a root of this polynomial. And we know that the only possible rational roots of y cubed minus 30 are the divisors of number 30. So are plus minus 1, plus minus 2, plus minus 3, plus minus 5, plus minus 6, plus minus 10, plus minus 15, and plus minus 30 as well. Well, negative numbers can be excluded at hand, and you can verify that none of these numbers satisfy our equation. None of them satisfy y cubed minus 30 equals 0, so cube root of 30 must be irrational. It's the fastest way of proving it, probably. Okay, so it was the first problem. Second problem from this competition. We wish to compute the sum of all natural numbers n which are at the same time divisible by 18 and which satisfy this inequality. Binary logarithm of 2n plus logarithm with base 4 of 4n plus logarithm with base 8 of 8n is strictly less than 25. My hints for this problem: change the base of every logarithm to 2 using this well-known formula. Logarithm with base b of c equals logarithm with base a of c over logarithm with base a of b. Notice then that if a is an integer, the greatest integer in the interval from 1 to a divisible by number d is floor of a over d times d. And finally, recall that the sum of consecutive natural numbers is given by this formula. So give this problem a try. Okay, very nice. So let's do it. So first of all, we must assume that, well, n is strictly greater than 0 because logarithms. Okay, and now let's put everything on one side and let's transform it. So we have this number, and let's transform it. First, I wish to use the law of logarithms. So binary logarithm of 2n is binary logarithm of 2 plus binary logarithm of n. Here we have this. Finally, this. Okay. Now, this is 1, this is 1, this is 1 as well. So we have 1, 1, 1, minus 25, so it will be minus 22. Now, I wish to change bases of my logarithms. So I can write this logarithm right here as binary logarithm of n over binary logarithm of 4. And I can write this logarithm as binary logarithm of n over binary logarithm of 8. And we have minus 22. Okay, what now? Well, binary logarithm of 4 is 2, and here we have 3. So I can write 1 plus 1/2 plus 1/3 times binary logarithm of n minus 22. So it's 11 over 6 times binary logarithm of n minus 22. And finally, I can factor out 11 over 6, and I have binary logarithm of n minus 12. And now we know that this number is less than 0 if and only if n is less than 2 to the power of 12, also known as 4096. 4096. All right. Well, and now we wish to find the sum of all numbers between 0 and this number which are divisible by 18. So integers in interval from 1 to this number, inclusive, divisible by 18, which are, well, it's 1 times 18, it's 2 times 18, 3 times 18, and so on. The last, as I suggested, is floor of 4095 over 18 times 18, and this last number happens to be, let me take a look, it's 227. So we have 227 numbers which are divisible by 18, and we want to sum them. So 1 times 18, 2 times 18, 3 times 18, plus 227 times 18. 18 can be factored out. So 1 plus 2 plus 3 plus 227. And now, using formula which I hinted at, it's 227 times 228 over 2, and after some calculations, it's 465,804. So it's our result. This sum equals exactly this number. Okay. Now, our third problem. We wish to sketch the graph of function f of h, f of x equals the absolute value of 3x plus 3 over x minus 2. And then we wish to answer for what values, I should say plural, values of m, does f of x equals m have two solutions x of the same sign. My hint for this problem: try to write this homographic function as q plus a over x minus 2 for some a and q. And if you do that, asymptotes should be obvious from this form. Vertical and horizontal asymptotes should be visible. And you may wish first to draw the graph of this function and then function with absolute value. So give this problem a try, and I will see you in just a minute. All right. So as I suggested, let's take 3x plus 3 over x minus 2. I will do a trick. I will write 3x minus 2 right here, but I have minus 6 and I should have plus 3. So I need to add 9 over x minus 2. So it's 3 plus 9 over x minus 2. And now two things are visible. The vertical asymptote of, let's call this function g. It's g of h, same. Well, it's given as x equals 2, because clearly x cannot be 2. And the horizontal asymptote of g, well, if x goes to either plus or minus infinity, this fraction goes to 0, and we are getting closer and closer to number 3. So it's y equals 3. And now I have prepared the graph in advance because I'm not too good at writing. Sorry about that. Yeah, so here I have a professional graph of my function f of h already with absolute value. So what happened here? Well, first I have sketched the asymptotes of my function. Here is vertical asymptote at x equals 2 and horizontal asymptote at y equals 3. And then what you need to do basically is take a couple of points. For example, check the value of 1, check the value at 0, at -1, -2, and so on. Try to sketch these points and then try to connect them in a continuous motion of your hand, because we know that this function is continuous. As I said, this function is already with the absolute value. Without the absolute value, this function would go here, but absolute value sort of flips the graph below y-axis, x-axis, to be above x-axis. So this graph looks like that. Very nice graph. And now the second part of our problem. For what values of m does f of x equals m have two solutions of the same sign? Two solutions of the same sign. So we are considering horizontal lines, and we wish to write on which heights does these lines intersect our graph at 2 points of the same sign. So for example, if I take this line y equals m, well, we have, for example, two x's. They are both negative. So our condition is satisfied. And it should be visible. This point of intersection right here is 1.5. So we have two solutions of the same sign. So let's write it. F of x equals m has two solutions of the same sign if and only if well, let's take a look. We must go from 0, so m must be greater than 0, obviously, because at 0 we have only one solution, up to 1.5. On 1.5 we have one negative and one solution of 0, so 0 has no sign, so it's not good. And then, if you look closely, at 3 we have only one solution, because this part of a function goes to its asymptote. But beyond number 3, again, we have two solutions. Maybe let's maybe it's not visible from my graph, but everywhere beyond number 3, above 3, we have two x's. This time both of them are positive. So it's union 3 plus infinity. And it's the solution. Let me erase my yellow lines. And yes, here is the graph, and here is answer to the second part of the problem. Okay, now, fourth problem. Find the range of this function. G of h is given by geometric series 1 plus 4 over x squared plus 16 over x to the 4th power plus 64 over x to the 6th power, and so on. In the original problem statement, it was stated that this is convergent geometric series. So, hints for this problem. Geometric series 1 plus q squared plus q cubed, and so on, converges if and only if the absolute value of q is less than 1. And if it is less than 1, then we have an explicit formula that this converges to 1 over 1 minus q. So give this problem a try, and I will see you in just a minute. Okay, so as I suggested, 1 plus 4x squared plus 16 over x to the 4th power, and so on, is a geometric series. It converges if and only if, well, the ratio should be strictly less than 1. We can omit absolute value because this ratio is obviously a positive number. So in other words, 4 is less than x squared. So factorization x minus 2, x plus 2. So we have a quadratic function with zeros minus 2 and 2, and it is positive on the interval minus infinity minus 2 union to infinity. So it's sort of the domain of our function. So it's the domain of our function. Let's write it. Domain of our function g equals that. I won't write it. Okay, and now in this domain, g of x can be written as 1 over 1 minus 4 over x squared, or 4 over x squared less than 1. Yes. And now I wish to play some type of game, because you can find the range using mathematical analysis, calculus, derivative, and so on, but we can do something less scary to be said. So let's take a look. 4 over x squared is obviously between 0 and 1, obviously. So if I put a minus in front, it's greater than minus 1, but less than 1. If I add 1, it's a number between 0 and 1. And now, if I take a reciprocal, reciprocal of 1 is 1, reciprocal of 0 is plus infinity. And actually, crucially, every value is attained between these two values because of the intermediate value property, for example. And now it is visible that the range of our function is interval from 1 to infinity. So range of g equals 1 infinity. It's the fastest way probably of finding the range. Okay, so it was the last problem for 10 points. Now we will be solving harder problems. Let's start with problem number 5. A trapezium is inscribed in a circle of radius r. One of the bases of this trapezium is the diameter of a circumcircle. Prove that this trapezium is isosceles and is the easy part. Find the measure of the interior angles of this trapezium, whose area is the greatest. By the way, I mean trapezium as in British English, so it's a quadrilateral which has two parallel sides, at least two parallel sides. In US English, it's probably called a trapezoid, something like that. Here are my hints for this problem. Recall that the angle subtended by a diameter of a circle is a right angle, is right. Then this interior alternate angle theorem, probably what it's called. If I have two parallel lines, if I intersect them by a third line, these two angles marked in green are equal. And for the second part, I suggest to use mathematical analysis. Let alpha be one of the angles of our trapezium. Express everything in terms of r, which is a constant, and cosine of alpha and sine of alpha. And I suggest to consider square of this area and do substitution, u equals sine squared of alpha, to make differentiation simpler. It can be done obviously without this substitution, but it will make our lives easier. So give this problem a try and make a good drawing. I have made a good drawing in advance. So give this problem a try and I will see you in just a minute. Well, wait a minute. Perfect. Okay, so I have made this drawing. I have my trapezium. First, I wish to prove that it is isosceles. Well, I will do it by angle chasing. I have marked, by the way, I have marked my vertices of my trapezium by A, B, C, D. The center of this circumcircle as capital O, and I have marked these perpendicular projections of points C and D on the line AB as D prime and C prime. And also I have extended segments AD and BC to the point of intersection, which I marked E. Okay, and now I wish to mark a few angles. First, let's mark this angle alpha. This angle is alpha. Well, as I suggested, the angles subtended by the diameter of our circle is right. So this angle right here is right. So since there is alpha, here we have 90 degrees minus alpha. Very well. 90 degrees minus alpha. Now let's take a look. Since this angle is 90 degrees minus alpha, or you know what, let's write it in radians. Pi over 2 minus alpha. This angle right here is also pi over 2 over alpha. Why is that? Because we have two parallel lines intersected by the third line, So these two angles are the same. Very well. And moreover, here is pi over 2 minus alpha as well. Why is that? Well, because these are two angles subtended by the same arc. Yes, this angle and this angle. So they are equal. It's a well-known property. What else? Well, here also we have right angle. And what else? Well, since we have pi over 2 minus alpha right here, we have also pi over 2 minus alpha right here. Again, because they are subtended by the same arc. Very well. And that means also notice that this angle is the same as this angle. Again, they are subtended by the same arc DC. So, since these angles are the same, these angles are also the same, this entire angle right here must be also alpha. Which means since alpha is at the same time measure of angle A and measure of angle B, triangle BEA is isosceles. Because this triangle has two same angles at the base AB. Okay, very nice. But now, since AB is parallel to DC, triangle CED is also isosceles. And that means, let's mark it asterisk, double asterisk. By one asterisk, we know that BE equals EA. And by double asterisk, we know that CE equals ED. And if we subtract these two equalities, we get that BE minus CE equals EA minus ED. But what is BE minus CE? Is AD or DA. No, it's BC. Sorry, it's BC. BC and BC equals DA. So our trapezium is isosceles. So ABCD is isosceles. It has the same segments BC and AD. So that closes the proof of our first part of the problem, the easier part. Well, in general, this is also true for every triangle, for every trapezium inscribed in a circle, not only for trapezia whose one of the bases is the diameter, but it is what it is. And now I wish to do to solve my second part. So I wish to find the measure of angle alpha for which the area of this trapezium is the greatest. And I will erase some lines to make my drawing clearer. I will erase this, and this. Okay. Now, I wish to do some trigonometry. Notice the following. AB is 2 times R by assumption. And triangle BDA is a right triangle. So by using basic trigonometry, DA can be expressed as AB times cosine of alpha. Yes. The ratio of this length to this length is cosine of angle alpha, which means that it's 2R cosine of alpha. Very well. What else? Well, we have another right triangle, triangle AD'. It's also a right triangle. So DD prime or D'D, well, it can be expressed this time as dA times sine of alpha. dA times sine of alpha, but the dA is 2R cosine of alpha. So we have 2R cosine of alpha, sine of alpha. And finally, let's look at AD prime. We have this right triangle. AD prime, it's the cosine of alpha times dA. And the same holds for C prime B. It's dA times cosine of alpha. dA is 2R cosine of alpha, so it's 2R cosine squared of alpha. Okay, and that means in turn that the second base, CD, well, what is CD? CD is AB minus AD prime minus C prime B, so it's 2R minus 4r cosine squared of alpha. Okay, and now we can write the area of our trapezium as a function of variable alpha. So our area can be written 1/2 AB plus CD times d'd. Okay, AB is 2r, CD is 2r minus 4r cosine squared of alpha, and d'd, it's 2r cosine of alpha sine of alpha. Now we can simplify this formula quite a bit. So I can write it as 4r squared. Let me take a glance at my notes because I want to get it right. It's 4r squared 1 minus cosine squared of alpha, cosine of alpha, sine of alpha. And 1 minus cosine squared of alpha, this part, it's sine squared of alpha. So we can write our result as 4r squared cosine of alpha sine cubed of alpha. And let's also take a look at the domain of our function. Which angles are possible? Well, it should be visible that the angles which are possible are between 45 degrees and 90 degrees. Why is that? Because if we have angle of 45 degrees, our trapezium reduces itself to a triangle. And if we have an angle of 90 degrees, well, almost 90 degrees, it looks almost like a rectangle. So alpha is somewhere between pi over 4 and pi over 2. Okay, and now we wish to maximize this area. How can we do it? Well, I suggest to not to get bogged down with too difficult differentiation. I consider the following. Let's consider the area squared of our trapezium. It's 16r to the 4th power cosine squared of alpha sine to the 6th power of alpha. Well, and now cosine squared of alpha is 1 minus sine squared of alpha sine to the 6th power of alpha. And now let's make a substitution. Let u, for example, be equal to sine squared of alpha. Well, since alpha is between pi over 4 and pi over 2, u must be between where? Well, if alpha is pi over 2, we have 1. If alpha is pi over 4, we have 1/2. Okay, and now let's consider function f of u, which equals just this part, but with substitution. So it's 1 minus u cubed, also known as u cubed minus 4u to the 4th power. Let's differentiate it. F prime of u, it's 3u squared minus 4u cubed, and we can write it as 4u squared or minus 4u squared u minus 3 over 4. And now we see that I need a new page. That's the first thing we see, that I need a new page. Okay. And now we see that f attains its maximum at u equals 3 over 4. Why is that? Well, because on the interval from 0 to 3 over 4, our derivative is positive, and from 3 over 4 to 1 is negative. So we can write that area of our trapezium is the greatest if and only if u equals 3/4, but what was u? U was sine squared of alpha. Sine squared of alpha, so sine should be equal square root of 3/2, which means that alpha is 𝞹/3. 60 degrees, in other words. So our answer, the dimensions, the angles of our trapezium should be 𝞹/3, 𝞹/3, 2𝞹/3, 2𝞹/3. For these angles, the area will be the greatest possible. Okay, so that closes this problem. And now, the most interesting problem of this competition from combinatorics. Let Pn be a regular n-gon, where n is greater than or equal 3. Our problem has 4 parts. Part A. How many right triangles are there whose vertices are some vertices of Pn? A prime. How many non-congruent right triangles are there whose vertices are some vertices of Pn? B. How many scalene triangles are there whose vertices are some vertices of Pn? And B prime. How many non-congruent scalene triangles are there whose vertices are some vertices of Pn? So it's a problem from combinatorics. It's a very nice problem. Solution is not that trivial. Here are my hints. The angle subtended by a diameter is right, and no other angle subtended by a chord is right. It's the only, if we have a circle and we subtend some angle, the only possibility for it to be right angle is that chord subtending this angle is diameter. For A prime, consider separately cases where, first of all, where n is odd, when n modulo 4 is 0, and when n modulo 4 is 2. Part B is much harder. You should consider 4 cases. When both 2 and 3 do not divide n, where 2 divides n but 3 doesn't, where 2 doesn't divide n but 3 does, and finally when 6 divides n. The symmetry group of a regular n-gon is of order 2n, because we have 2n rotations, and we can also reflect some vertices. And finally, you can simplify your answer by using floor function and Iverson's bracket. If you are not familiar, it's not completely standard, but Iverson bracket of a formula, it's either 0 if formula is false, or 1 if this formula is true. It's written in square brackets. It's a nice notation. Give this problem a try, and I will see you in just a minute. Okay, so here is, first of all, let's consider first, I have made some drawings. Let's consider first part A and A prime. Here I have a regular 9-gon, for example, with odd number of vertices. Notice that if, let me make it smaller. Perfect. Notice that if 2 does not divide n, then none of our diagonals is a diameter. None of the diagonals of the n is a diameter of our circle, which means that it's not possible to get a right angle, because to get a right angle we must have a diameter. So it is impossible to form a right triangle. To right triangle, let's say. Okay, so in other words, the answers to parts A and A prime is 0 if 2 doesn't divide n. Okay, now, more interesting case, if 2 does divide n. We have two subcases, and I have made my drawings. So, but I will use them in a minute, because part A, let's take a look at, for example, sorry about shuffling things around, but I need to have some space. Okay, so for example, here in the blue, I have a regular tengon, decagon, as it is called, probably. How many right triangles can be formed? Well, first of all, we need to choose a diameter. In how many ways can we choose a diameter? Well, we need to choose two vertices opposite of each other. So we can do it in n/2 ways. n/2 ways to choose a diameter. And then, once diameter is chosen, once our diameter is chosen, we need one of the rest n-2 vertices to form a right triangle. For example, if I take this vertex, I have right triangle right here. So n/2 times a-2 is the number of different triangles. So maybe let's write some comment. n/2, the number of ways, to choose a diameter, and we need the number of ways to choose the third vertex. So we have our answer for part A. Part A can be written succinctly in this form. It's n times n-2 over 2, provided that 2 is even. So Iverson bracket 2 divides n. If 2 doesn't divide n, it's 0. If 2 does divide n, it's n times n-2 over 2. So part A was quite simple. And now part B is harder, because now many of the triangles which can be formed are congruent to each other. And we are asked how many non-congruent triangles are there. Let's take a look once again. Now, I will split my reasoning into two subcases. Case number 1, so it's for part A prime. Case number 1 is when n modulo 4 equals 2. So for example, a regular decagon, as it was considered. How many non-congruent triangles are there? Well, if we are considering non-congruent triangles, right triangles, we can first choose one diameter, just one. So I will choose one diameter, let's say this one. And now it's crucial to drop a perpendicular bisector of this segment. And now notice the following. We have n vertices, and we have 4 groups of vertices. Notice that here we have n minus 2 over 4 vertices. Likewise, here we also have n minus 2 over 4 vertices, here as well, and here as well. It sums up to n. Very well. And now, form non-congruent triangles, we just need one vertex from one of these groups. Why is that? Well, because notice the symmetry. If I take this triangle right here, it's a right triangle. if I take this vertex, we form a triangle with different angles, with bigger angle right here. So these two triangles are not congruent. But for example, if I take vertex from the other side, right here, well, then these two triangles are congruent. So I need just one vertex from one of these groups. So how many ways is to do that? Well, it's just n-2/4. So it's the number of ways to choose one vertex from one of the four groups. One of four groups. Very well, so it's our answer. And it can be simplified. It's exactly the same as n/2 floor of n/2. You can verify it, that it's in fact as I have written. Okay, second case when n modulo 4 is 0. So we have a number of vertices divisible by 4. For example, a regular dodecagon, 12gon. Something like that. Now, I wish to do something similar. First, we need a diameter. So let's say here we have our diameter. And now I wish to drop perpendicular bisector once again, but this time this perpendicular bisector will go through two of the vertices. Okay, and now let's take a look. Here we have n-4/4 this time, vertices. Here we have n-4/4, here as well, and here as well. And how many ways are there to form a right triangle? Well, we just need one of the points from these groups, or we can also choose this point right here. So there are n-4/4 plus 1 ways, which is n/4. And n/4 is the same as floor of n/4. So again, this number, we choose one of the points from one of four groups, or one of or vertex or vertex which lies on the perpendicular bisector of our diameter. Okay, so in both cases it's floor of n/4. Provided that n is even. So we can write our answer to part A prime. The answer is n/4 in floor, but provided that 2 divides n. If it doesn't, there is 0 such triangles. Okay, so I hope that makes sense. Now, part B, it's harder, because we will be counting scalene triangles. So, in other words, triangles whose sides are of not equal length. And I will do it in the following way. We will have two subcases. Let's start with maybe we'll have in fact more subcases than 2, but okay. Well, so first of all, I wish to first enumerate isosceles triangles, because I will take every triangle, number of triangles which can be formed, and I will subtract the number of isosceles triangles, and I will have the number of scalene triangles. Okay, how many isosceles triangles can be formed? Well, it depends. It depends. Maybe okay. So we have 4 cases. Case number one. Let's consider case number 1 when 2 doesn't divide n and 3 doesn't divide n. So for example, 9 gon. Sorry, wrong polygon. Wish to have this one. It will be for later. Okay, 9 gon. How many isosceles triangles can be formed? Well, first notice that every isosceles triangle can be formed by first choosing one vertex. For example, this vertex. How many ways are there to choose a vertex? Well, n ways. And then I make a diameter. And now, since n is odd and 3 doesn't divide n, I need just one more point to form an isosceles triangle. So for example, one point from this group. How many points are there? Where there are n minus 1 over 2 points. I need just one of them to form my triangle. For example, if I choose this one, then automatically I must also choose this one, and I form an isosceles triangle. So it's n times n minus 1 over 2. And notice that since, well, you may ask why this second assumption? Well, if this is the case, there are no equilateral triangles. So every triangle, every isosceles triangle can be found uniquely, first by choosing this point and by choosing 2 points such that these 2 segments are of the same length. Every such triangle is counted once and only once. Second case. Case number 2, where 2 divides n, but 3 doesn't. How many ways are there to do it? Well, here we have, for example, decagon, our decagon. The same story. First we choose a vertex, for example this vertex, n ways to choose a vertex. Then we drop a segment, but this time points in this group, how many points are there? N minus 2 over 2 this time. So I need to choose one of these points to form an isosceles triangle. For example, if I choose this point is chosen automatically, and I form this triangle, which is isosceles. Okay. Case number 3. 2 doesn't divide n, and 3 does divide n. Now, there is a slight variation. It's the same as in case 1, but now we have equilateral triangles, and every equilateral triangle is counted thrice in this formula. Thrice. Because if you have an equilateral triangle, you can say that you start with this point and then you choose these 2 points, or you can say that you start with this point and then you choose these 2 points, or that you choose this point first and then these 2 points. So we are counting multiple times the same triangles. How many equilateral triangles are there? Well, there are n over 3 equilateral triangles, and we need to count every one 2 times and to subtract them. because here they are counted 3 times, so we need to subtract 2 times the number of equilateral triangles. Okay, and well, why n over 3? Why n over 3? Because when we have, for example, a hexagon, notice that if I choose one vertex, we have automatically just one equilateral triangle which can be formed, and each of them is counted 3 times, so n over 3. And finally, case number 4. 2 divides n and 3 divides n. The same story as in case 2. It's n minus 2 over 2, but we need to subtract the number of equilateral triangles. Yes. So it's 2 times the number of equilateral triangles. Well, so we have 4 separate cases. Is there a nice way to combine them? Yes, I leave it to you. It can be easily demonstrated that the general formula and the answer to this part, to part B, it's n floor of n minus 1 over 2 minus 2n over 3, but provided that 3 divides n. It's the general formula. You can verify it very easily that it is in fact the case. So, sorry, it's the number of isosceles triangles. Yes, the number of isosceles triangles. Isosceles triangles. And how many non-isosceles triangles, scalene triangles? Well, how many triangles are there where n over n choose 3? Because we need to choose 3 points, and we need to subtract the result above. So it's the number of scalene triangles. The number of scalene triangles. And it's our answer to part B. It's our answer to part B. But this time, part B prime is much easier. How many non-congruent scalene triangles are there? Well, notice that if we have a triangle which is scalene, we can rotate it in how many ways? In n ways. I can rotate it. Yes, for example, if I have a triangle, like that, I can rotate it n times to get each time a congruent triangle, and also I can reflect it. And also I will get a congruent scalene triangle. So we have n rotations, symmetries, so we have to divide by 2n, and it's our answer for part B. Part B is n choose 3 minus n minus 1 over 2 floor plus 2n over 3. 3 divides n, but it's divided by 4n. And it can be simplified. I leave the details to you, but it can be simplified to this form. Need some space. Plus 1/3 3 divided. So this is the number of such triangles which are not congruent to each other. And that closes our problem. Truly beautiful problem. Many cases, not that easy. It's the best problem on this test. Okay, and now, last problem from analytic geometry. Problem number 7. Let L be a line given by this equation, 2x minus y minus 3 equals 0, and let capital omega be a circle given by this equation, x squared plus y squared plus 4x minus 6y minus 12 equals 0. Line L intersects circle omega at points A and B. Let C be the center of this circle. We wish to find the equation of the incircle of a triangle ABC. So this problem is not very hard, but my hints. This problem can be very tedious and hard if you don't know useful formula. Well, what's the easiest way to find the area of a triangle in coordinate system? Well, it's to compute 1/2 the determinant of two vectors. And obviously absolute value has to be given. What's the fastest way to find the in radius of a triangle? Well, once you have area is the semi-perimeter, P is semi-perimeter of our triangle times in radius, sorry. And what's the fastest way to find the incentre? Well, you may not know this formula, but in center is given by this formula: A times point A plus B times point B plus C times point C over A plus B plus C, where A, B, C are length of our triangle and capital A, B, C are coordinates of the vertices. It's the quickest, best way to find the incentre. In fact, after finishing this problem, I will prove this formula as a sort of addendum. So give this problem a try. Okay, so here is my solution. First, let's transform the equation of this circle omega. So let's take x squared plus y squared plus 4x minus 6y minus 12. I wish to do some manipulations. I will put x squared plus 4x. I will write plus 4. Then I will write y squared minus 6y plus 9. And I have introduced plus 13. So I have to subtract 25 to balance my equation, to balance my expression. So it's x plus 2 squared, y minus 3 squared, minus 25. And now it should be visible that the center of this circle, so point C, is minus 2, 3, and the radius of omega is 5. It's 5. Okay, very well. So we have found our point C. What about A and B? Well, to find A and B, we need to solve, so points A and B are described by the following system of equations: 2x minus y minus 3 equals 0, and x squared plus y squared plus 4x minus 6y minus 12 equals 0. We need to solve this system of equations. Notice that from the first equation, y equals 2x minus 3, and we can put it in our second equation. X squared plus 2x minus 3 squared plus 4x minus 6 2x minus 3 minus 12 equals 0. And now, after many simplifications, it's a rather easy quadratic equation. It's 5x minus 20x plus 15 equals 0. You can factorize it quite easily. X minus 1, x minus 3 equals 0. And so either x is 1, if x is 1, y is minus 1, or x is 3 and y is 3 as well. And without any loss of generality, we can say that point A is this first point and point B is this second point, without loss of generality. You can also change A to be this point, B to be this point, doesn't really matter. Okay, and now it's not necessary, but I made a graph, I made a drawing of this situation. So here's my drawing. Points A, B, and C are sketched. We have our circle omega, and what we wish to do is find capital I, the incentre of this triangle ABC. So it has two parameters, R and I as well. Okay. First, I wish to find the area of my triangle ABC. And to do it, well, area of triangle ABC, notice that it can be written as 1/2 the absolute value of determinant of two sides. So for example, determinant of vector, of which vector, which will be the easiest. Let me take a look. Doesn't matter. Doesn't really matter. BC and CA, for example. Okay, so let's compute these vectors in advance. BC, CA. BC, CA. What is BC? Maybe let's write C. C was -2, 3. Okay, so what is BC? BC connects B and C, so it's -5, -5, 0. What is CA? CA is 3, -4. And finally, AB maybe will be useful. What is AB? AB is 2, 4. 2, 4. Okay. Okay, so this determinant, which we are computing, it's 1/2 the absolute value of determinant of matrix -5, 0, 3, -4. So it's 1/2 times 20. So it's 10. The area of our triangle is 10. Now, I wish to find length of these sides, A, B, C. Well, notice that A and B are obviously R omega, which was 5, because they are radii of our circle. What about C? C is the length of a vector AB. Length of vector AB, so it's 2 squared plus 4 squared, square root of 20, 2 square roots of 5. Very well. So semi-perimeter of our triangle, A plus B plus C over 2, semi-perimeter is 5 plus square root of 5. And now we can find the in radius. So remember that area is semi-perimeter times the in radius. So we can divide, equals R, and now we can simplify it. It will be 5 minus square root of 5 over 2. Okay, so now we know our small case R. And now I need a new page. Finally, incentre of our incircle can be found by this formula. So let's use it. It's a powerful formula because finding the incentre is usually not pleasant. It's slightly more pleasant for isosceles triangles, as in our case, but let's use this formula to make our lives easier. So it's 5 times capital A. What is capital A? Capital A is 1 minus 1 plus 5 times capital B, which is 3, plus C. What is C? C is 2 square roots of 5 over capital C. Capital C is minus 2, 3. And it's over 5 plus 5 plus 2 square roots of 5. All right. Now let's simplify it. So we have 5 minus 5 plus 15 plus minus 4 square roots of 5, 6 square roots of 5 over 10 plus 2 square roots of 5. And now we can simplify it. It's 20 minus 4 square roots of 5, 10 plus 6 times square root of 5 over 10 plus 2 times square root of 5. We can divide by 2. So we have 10 minus 2 square root of 5, 5 plus 3 square roots of 5, 5 plus square root of 5, and let's multiply by 5 minus square root of 5. And let's multiply everything. Here we have 20 in the denominator, and in the numerator, what do we get? The first coordinate is 50 plus 10. 50 plus 10. Let me take a look. 50 minus 10 square root of 5 minus 10 square root of 5. Second coordinate is, I multiply this by that, and I have 25 minus 15 plus 15 square root of 5 minus 5 square root of 5. Okay, it's over 20. Calculations, and now we have 60 minus 20 square root of 5, comma 10 plus 10 square root of 5, it's over 20. So finally, it's 3 minus square root of 5, 1 plus square root of 5 over 2. So it's our incentre of our triangle ABC. So if I mark my encircle by lowercase omega, our equation, it's x minus 3 plus square root of 5 plus y minus 1 plus square root of 5 over 2 squared equals r squared. What was r? Well, r is this number, 5 minus square root of 5 over 2. And this is our answer. And that closes my solution of these problems. Before we go, if you wish, I wish to prove this formula for incentre of a triangle, because it's a very handy formula, but how to prove it? Because you may be not familiar with it, you may see it the very first time. What is the proof? Well, as a lemma, as an addendum, I will prove this formula which I used. So let ABC be a triangle. A equals length of BC, B equals length of CA, C equals length of AB. then the incentre I is given by this formula which I used. And how can we prove it? Well, we will prove it by using dot product. Because remember that the incentre is the point of angle bisectors. It's the point of intersection of angle bisectors. So what I wish to do is to show that, for example, this angle and this angle are the same when I define I by this formula which I have written. And now notice that the following conditions are equivalent. I will write equivalent conditions, and the last one, the very last one, will be true. So the first one will also be true. Okay. The following conditions are equivalent. Measure of angle CAI equals the measure of angle AAB. Well, since these angles are acute, notice that it's not acute, they can also be obtuse. It's equivalent to saying that cosines of these angles are the same. It doesn't really matter that they are acute. Doesn't matter. Okay, it's equivalent. Now, how can we find cosine of an angle? Well, the best way is to do a dot product. Cosine of this angle is AC, vector AC, dot product AI, ACAI over length of AC times length of AI equals cosine of EAB. Well, what is it? Well, it's dot product of AI and AB over AI times AB length. Now, we have some common parts. So first, let's write it as that. What is AC? Well, AC is just AC. And what is AI? AI, or maybe, you know what? No. Let's leave it as it is for now. AI and AI and AI are gone. They are the same. So I can multiply by AB. So AB times that should be equal AC times that. Okay. And now, what is AB? AB is C, length of side C. And now AC. Maybe I will write, you know what? I will write it as C times AC dot product AI C times AC dot product AI minus AC times AB. But what is AC? AC is B dot product AI. Should be equal 0. Okay, and now here we have AI, here we have AI. We can factor it out. So CAC minus BAB dot product AI. Is it 0? That's the question. Let me just take a look at my notes. Is everything right? It is probably. Okay. CAC minus BAB dot product. What is AI? Well, AI is a segment. It's a vector connecting A and I. But I is AA, BB, CC over A plus B plus C minus point A. Okay, now I can get rid of this denominator. CAC minus B times AB dot product A BB CC minus AA minus BA minus CA equals 0. It's equivalent. CAC BAB dot product, and now some cancellations can be noticed. AA gone, so it's B times B minus A plus C times C minus A equals 0. And now AAC minus BAB dot product. What is B minus A? Well, it's a vector connecting A and B. And I will do slight trick right here. I will write minus here, and I will put A minus C right here. What is A minus C? Well, no, sorry, I won't do it. What is C minus A? It's C times AC equals 0. Is it true? Now we can multiply everything with everything. So we have BC AC dot product AB. What else? We have plus C squared AC dot product AC. I have B squared AB dot product AB. And finally, minus BC AB dot product AC equals 0. And now let's take a look. This and that, they are the same, because dot product in real numbers is commutative. Moreover, what is AC dot product AC? Well, it's B squared. It's because we know that some vector dot product with itself is the norm squared of this vector. A norm of this vector is B. And what is AB dot AB? Well, it's C squared. It's C squared. So we have C squared B squared minus B squared C squared equals 0, which is true. 0 equals 0. And as I said, all these equations were equivalent. So since the very last one is true, this condition is also true. Which means that point I lies on the bisector of angle A. And you can do similar reasoning to show that it also lies on the bisector of angle B, which means that it's in fact in center of this triangle. So similarly, I lies on the bisector of angle B, so I must be the incenter of triangle ABC, which closes the proof of my lemma. So it's true. And to be honest, that's it. We have reached the end of our video. Thank you for watching. Thank you for sticking with me. As I said, tomorrow there will be second round of this competition. So in a couple of days, once the problems are published by university, I will also probably cover them as a sort of mental activity. Because as you have seen, apart from problem number 6, the rest of the problems are typical, very typical. Maybe they are slightly higher than normal high school problems, but they are nothing special. That's it. Thank you very much for watching, and I will see you next time. Goodbye.